In this section, we're going to start to look at more user-friendly definitions of limits, and things are hopefully going to be a little bit easier to digest. So the formal definition of a limit, not to be confused with the precise, the epsilon delta definition of a limit here, says suppose that a function f is defined for all x near c except possibly at c. If f of x is arbitrarily close to L for all x sufficiently close to c, we write limit as x approaches c of f of x equals L and say that the limit of f of x as x approaches c is L. Holy smokes here, that's a lot. What I would focus on for this is I would focus mostly on this informal definition down here. I think this is a lot easier to understand, and this is how I think about limits. So our informal definition that we're going to be used going forward says that we say that the limit as x approaches c of f of x equals L if f of x, and remember that f of x here, when we say f of x, it might be helpful to think about the y value of your function here, gets closer and closer to L as x gets closer and closer to c from both sides of c. This is going to be really, really important. So the way I visualize this is I think about, okay, if I were to trace my function from both sides, so if I was to trace this function from the left-hand side over here, as I get closer and closer to this x value down here, what y value am I getting closer and closer to? Well, in this case, I'm getting closer and closer and closer to L, to this guy over here from the left-hand side, and then this also needs to be true for the right-hand side as well. So as I approach from the right-hand side over here, as I trace my function and get closer and closer and closer, visualize your function getting closer and closer from this side and getting closer and closer to this side. As we get closer and closer on both sides, right, this side and this side, what y value? Well, in this case, we're getting closer and closer to L here, which means that L is our limit. One thing I will make sure to draw special attention to, I'll actually point to this formal definition here. It says f is defined for all x near c except possibly at c. So this is actually one of the more confusing aspects of limits, is that your function does not actually even need to exist at this particular x value in order for the limit to exist. And this is probably going to be one of the tougher things to kind of wrap your mind around here. And I can actually show in this example that I've drawn right here. Here I have a hole at x equals c. I have a hole right here at this particular point in my graph, but the limit still exists. The limit is equal to L. So we need to draw a little bit of separation between the value of the function and the limit of the function, because these can be two very, very different things. They tell us two very, very different things. We like it when they're the same. That leads to some very nice properties, but it is not required. It is not always going to be the case. So let's look at an example down here. It says use the graph of f of x to define the following values. So here I have f of 1 and limit as x approaches 1 of f of x. I'm going to look at parts a and b first. So I'm talking about what is the behavior right here at x equals 1. So f of 1, I would just look at what is the value of my function here. In this case, my function exists right there. I can tell because of that closed circle. I'm just going to ask myself, well, what's the y value of the point right there that I've circled? Well, the point, I should be more specific, this point right here, the y value of this point looks like 4. So f of 1 is equal to 4 here. The limit then, I'm going to try and trace with my highlighter here. If I come at this function from both sides, if I come at it from the left-hand side and if I come at it from the right-hand side, if you visualize almost like, you're driving on tracks, right? If you're approaching the same y value from the left-hand side as you are from the right-hand side, it looks like I'm still approaching that same point right there. Well, what y value does that point have? We're getting closer and closer to a y value of 4. So in this case, my limit is also 4 here. So we like it when this happens. This is actually something we're going to talk a little bit more later on in the chapter. It's called continuity. We really like it when this happens. Functions that are continuous have really nice properties, and we can do cool calculus stuff with them. But let's go ahead and look at 4 here. So 4, I'm looking at x equals 4. It says f of 4. What's the value of my function at 4? So for this, I'm looking, here's x equals 4, and I'm looking at this point right here, and I would say, well, it does look to me kind of like a y value. My graph's not perfect, but it looks like a y value there of -1. But that open circle, remember, that denotes a hole, which means that my graph does not exist at those points. The graph does not exist at those points. So what that means for me, there's no closed circle anywhere to denote that my function exists at 4. When I talk about 4, I can say either that this function does not exist. I use DNE for short, mostly just because I'm lazy. Or you could say that our function is undefined here, undefined. Either one of those is perfectly fine. If you want to stick to one or the other, that's fine. I don't need to see them both. And which term we use might just depend on, what website you're looking at or what textbook you're reading. They both mean exactly the same thing here. Now this is going to be a little bit different though than the limit. Let me erase this right here. Oops. Okay. So if I look at the limit now, if I come at 4 from both sides, so if I come at it from the left-hand side, if I trace this function, even though the function does not exist at that point, I'm getting closer and closer and closer to my y value, which looks like should be about -1. So I'm getting closer and closer and closer to that y value of -1. I then also need to check the other side. So I'm going to check that other side, and as I approach from the right-hand side, I'm getting closer and closer again to that hole where my function doesn't exist, but that doesn't matter. I'm getting closer and closer to that point. So here I would say that my limit as x approaches 4 is equal to -1. So this is one example where we can have the function actually does not exist at a particular value, but the limit does. So this is a really good example that'll hopefully help us draw some distinctions between those two things. Let's look at -2 next. Here I have f of -2 and the limit as x approaches -2 of f of x. So let me change my color and let me erase a few things here. Let's get rid of this stuff here. All right, so I'm looking at -2. Oops. I'm looking at -2. F of -2. Now, there's some kind of interesting behavior happening here at -2. I've got this jump here. Remember that an open circle means that the function does not exist at that point. That's what we call a hole in the graph, so our function actually does not exist right here. A closed circle, however, means that my function does exist at that point. So if I'm looking at f of -2, what that's really asking is, hey, what's the value of our function when x is equal to -2? What's the y value? Well, I would look at this point right here. I would say, well, my y value is 1, 2, 3, 4, 5. So f of -2, oops, that's not -5, that's +5 right there. So my f of -2, my function at x equals -2, has a y value of 5. Limit as x approaches -2. So now I'm going to come at -2 from both sides. Let me erase this, oops, just a little bit and see if I can. Okay. So here I'm going to come at it from both the left and the right hand side. So if I come at -2 from the left hand side, so if I come at it from this direction over here, I want to ask myself, where is my function going? You can almost cover up the behavior at exactly -2. I just want to know, where does it look like the function's going from this side? If you were to almost cover up, and maybe I'll even do that, if you were to ignore all of this over here, right? If you just said, okay, what would you predict my function to be, even if I didn't know whether that was a point or not, you would say, well, it looks like that's approaching a y value of 3. So, okay, looks like my limit from the left-hand side in this case is 3. However, if I come at my limit, or excuse me, if I come at -2 from the opposite direction, if I approach -2 from this side over here, here I'm approaching this closed circle. I'm approaching this closed circle which has a y value of 5. I'm approaching two different y values. Now, limits are kind of like functions in that we don't like it to have more than one value. We want it to be a definitive, it's either this, or the alternative would be that in this case this limit does not exist or is undefined. Either term, again, is totally acceptable. I'll probably just use DNE just because it's less writing for me. But because both sides of my function are not meeting up at the same y value, we have to say that that limit does not exist. So if you have a break in your graph, or like a jump like we have right here, the left-hand side kind of jumps up to the right-hand side. We jump from a y value of 3 to 5. Our limit does not exist here. So notice in parts E and F, I kind of have the opposite behavior that I had in G and H there. And G and H, or excuse me, in C and D, I had the function not exist, but the limit did. Here, vice versa is true. Now the function does exist, but the limit itself does not exist. G and H, I think this is going to be a really, really interesting set. Let me erase this right here. Okay, so now we're talking about -5. So f of -5, I remember that, okay, this open circle right here, I know that that means that my function does not exist at that point. That is a hole in my graph. So I'm not going to look there for the value of my function. I'm going to look for any closed circles, and I see this guy down here, this closed circle. So okay, what y value does that have? It looks like it has a y value of about 3. So my function at -5 has a value of -3. Now, it's going to be a little bit tricky, but we want to compare this to the limit now. So if I compare this to the limit, I'm going to come at -5 from both sides. So if I approach -5 from the left-hand side, if I follow and trace my function, if I move closer and closer, it looks like I'm getting closer and closer to that hole. I don't care whether the function exists there or not. All I really care about is what's the y value right there at that point. Well, the y value at that hole, at this point right here, right at this point right here that I've now shaded in, is 0. Do I approach the same thing from the right-hand side? Well, it looks like I do. Here, if I approach -5 from the right-hand side, I am also approaching that same point right there, that hole in my graph. So in this case, I have the limit as x approaches -5 of f of x. This is equal to 0 because that's what y value we're approaching from both the left and the right-hand side. So this is a really nice example to show that all of the different cases. So when I look at A and B, here we had kind of the nicest case. We had the value of the function was equal to the limit. This is a really nice case. We like it when this happens, but that's not always the case. Here in parts C and D, we had the function not exist, but the limit did. In parts E and F, we switch those two around and say, okay, now the function does exist, but in this case, the limit does not. And then in parts G and H down here, they actually both exist, but the value of the function is totally different than the value of the limit. We have two completely different values right here. So just be very, very careful as you're working through limits. I would encourage you to try a lot of these looking at graphs and evaluating limits. I think it's a really good way to develop an understanding of how to calculate a limit, and it gives you a more intuitive sense as to what a limit is, because it is a little bit difficult to separate the value of the limit from the value of the function. It is something you need to train yourself to be able to do. Let's look at one more example down here. Here we have a table of values. We'd like to create a table of values for the function f of x equals x minus 4 divided by square root of x minus 2, corresponding to the values near x equals 4, and then we'll use this table to make a conjecture about the limit as x approaches 4 of f of x. So here, I try really hard not to use the graphing calculator. I am going to cheat a little bit here. I have mine right in front of me. What we're really doing is we're going to be taking each one of these values and plugging those into our function. So f of 3.9. You would be saying, okay, well 3.9 minus 4 divided by square root of 3.9 minus 2. And we would go and calculate that value. So here in this case I've got 3.9748. So 3.9748. I would fill that in my table, 3.9748. Now, for those of you that say, okay, well, and I don't know why I have this question mark here, I really should have a 4. For those of you that might say, hey, well, why don't I just take 4 and plug that in? You can absolutely do that, but let's see what happens here. If I take 4 and plug this in, I've got 4 minus 4 in my numerator divided by square root of 4 minus 2. So in my numerator, 4 minus 4 is 0. In my denominator, square root of 4, that's 2 minus 2. I have 0 over 0. We cannot draw any conclusions about this. If we had, say, 0 divided by 1, that's equal to 0. That's no problem. If I have 1 divided by 0, or any number divided by 0, this is technically undefined. But if I have something like this, 0 divided by 0, I've got 0 in my numerator and in my denominator. If I have a case like this, this has a very fancy calculus name. This is indeterminate form. And really what this means is, well, the limit might exist there, but it might not. For our problem in this case, the function itself is actually undefined at that point. So if you wanted to graph that function, you would have a hole at that point. Or at the very least, your function would not exist at this particular x value. But what I want to do here is I'm going to take points on either side of 4 and plug those in, see what happens when I get closer and closer and closer to 4. So if I take 3.99, do the same thing, plug that into my function here, I'll get 3.9975. And if I take 3.999, plug that in, I've got 3.9997. So what we want to be thinking about is, well, what value does it appear that we are moving closer to? So what y value are we getting closer and closer and closer to? In this case, from this left-hand side, it looks like it's getting closer and closer to 4. But remember that we do have to check that other side. We want to make sure we check the right-hand side, make sure that we're approaching the same y value. So let's actually do that over here. Let me change my color. So if I take 4.1 and plug that into my function over here, I'll have, what do I have? 4.0248 for 4.1. If I take 4.01, plug that in, I'll end up with 4.0025. And if I take 4.001, plug that in, I'll have 4.0002. So if I come at this from the left-hand side, it looks like I'm approaching a y value of 4. Over here on the right-hand side, these numbers, these decimals are getting smaller and smaller. It looks like the y values here in this case are also getting closer and closer to 4. And then since I approach the same number from both sides, we can now safely say for our answer that the limit as x approaches 4 of f of x is equal to, well, what y value were we approaching on both sides? It would be 4 here in this case. So really what we're looking at is we don't necessarily care about what is the y value of the function. We care about what y value are we getting closer and closer and closer to. So do your best to kind of separate the value of the function and the limit in your mind. I think this is something that doing some practice problems and looking at some more examples will help you out with.